all good. We're gonna hopefully get through this this part on elements today. And this actually is a review slide, so you may not have this one. Yeah, you probably do. Looks like you have it right before isotopes. Okay. So we did this slide before, I think. It's very similar. We need to pick up where we left off, looking at an atom, and the parts of an atom. We're worried about the nucleus that is home to the protons and the neutrons and the electrons in a cloud outside the nucleus. So we're going to kind of count those particles some more. But remember, one important particle, well, they're all important, but the protons actually is what we call the atomic number. So we're going to be using that term. And in every science, every field, there's terminology you need to learn. And anytime you see atomic number, that's the number of protons in the center of an atom of a given type of element. And it's always going to be the whole number, and I've been kind of emphasizing actually that number happens to be red on this periodic table. It's that whole red number. That's the atomic number. Okay? So, now the thing about, we talked about this before, I think, the thing about electrons is basically they are massless. You know, we kind of just pretend like electrons don't weigh anything. Protons, on the other hand, actually weigh something we call 1 atomic mass unit. And the symbol for atomic mass unit is the symbol U. And sometimes I learned it AMUs, but it's really U now, so I don't know. I'm kind of transitioning. So a U, an atomic mass unit, is very small. So I kind of wrote down here an equivalency statement. How small is 1 atomic mass unit? Well, if you have 1 gram of material, which is kind of light, okay, then you have 6.022 times 10 to the 23rd atomic mass units. So it's very small. Okay. And then we talked about neutrons. We're going to be talking more about all of these today. Jessica. Either way. I think you're going to have to cross-reference, apparently. So the last subatomic particle are the neutrons. And it might seem like the neutrons don't matter, but they do. The neutrons actually also weigh 1 atomic mass unit. Okay? So, yeah. The neutrons are important because subatomic particles with the same charge don't like to coexist. And actually, I don't know if you're familiar with the what if on the internet, but basically they come up with strange, you're usually in physics, but science questions. And the what if question was something like recently, what if the Earth was just basically a bunch of neutrons and the moon was a bunch of electrons to kind of represent kind of an atom? And so the dude did the calculations and it just couldn't happen because those protons wouldn't want to coexist. And basically, to get all those protons the size of the Earth to hang out together, it would take more energy than is associated with the entire universe. Okay. When we talk about astronomy, we're going to talk about something called a neutron star. And actually, it's not protons, but basically, the protons and electrons of matter for a neutron star, I kind of go, neutron stars, oh, so crammed. Basically, that cramming has made the protons and the electrons turn into neutrons. So neutron star is a neutron soup. So anyway, okay, so that's the neutrons. All right, that all works. So I have 2 variations I want to talk about today, and they both start with the letter I, so don't blame me. Isotopes and ions. And they have to do with different numbers of little particles that make up an atom. Now, what doesn't change with isotopes and ions are the number of protons. Protons are stuck. Protons are stuck, okay? So with isotopes, okay, it has the same number of protons, but with isotopes, it's the neutrons that actually are kind of, we have different forms that are favorable for a given element, okay? That's isotopes. So I brought today, I think I sent these around before. Probably when it comes to isotopes, I guess they both do. I'll start one over here and one over here. This box right here, you can see a bunch of elements, and then actually underneath the element or next to the element is a whole number, okay? And these are all different isotopes of these elements, okay? So what is an isotope? So basically it has a different number of neutrons in the nucleus, That's it. Different number of neutrons in the nucleus. It's funny how in astronomy and in my general chemistry and my physical science, we've all talked about isotopes in the last few weeks. Okay. So if you've ever heard of carbon-14 dating, carbon, we all know carbon, right? It's an element. But 14 actually is one isotopic form of carbon that does some cool things. Okay. When it comes time for building bombs or building nuclear reactors using the element uranium, only one isotopic form of uranium works for that. And so if you've heard about uranium enrichment, basically they're trying to concentrate to get that one isotopic form. So isotopes are a player. If you go into the health sciences, sometimes they will have you take dye, okay, that has a particular isotope that actually they can pick up on their X-ray or whatever. Okay, so isotopes are a player. What are they? Probably, I don't say fancy, but elements, sometimes they have a lot of this isotope and not much of this isotope. So some isotopes are preferred. So an isotope has the same number of protons in the nucleus, just different number of neutrons. All right. So remember atomic number, I already talked again today. Atomic number is the number of protons in the nucleus of an atom. Okay, atomic number. Now mass number is the number of, again it does with the nucleus, but mass number you are literally counting protons plus neutrons. Okay, so mass number. Sometimes I kind of write it a little equation, and actually sometimes I even get out my calculator to do these. So mass number has to be a whole number, okay, and literally you are counting mass number is equal to number of protons, which has to be specific for a specific element, plus number of neutrons, okay, mass number, so it's a whole number. It seems like we might have the other day, maybe not, picked on the element helium. Okay, now I know this is helium because it's got 2 protons in its center. Probably the most common form of helium then has 2 neutrons. Okay, so for this, and let's go ahead and make it neutral, so I'll go ahead and give it 2 electrons. There's my little helium atom. Pretty awesome. So for this particular atom, I would say its atomic number is 2. Okay? Its mass number is protons 2 plus neutrons 2 for a grand total of 4. Okay, so that's it. So mass number is a whole number. It's a counted number of particles. Sometimes students want to skip right to, well, if, and I understand, but it probably won't get you down the road. I understand if each one of these particles weighs 1 AMU, right? Mm-hmm. Okay, so the whole nucleus, it seems like, should weigh about 4 AMU, and it does. Okay, so actually that's a kind of a ballpark weight of that atom. Ballpark. Let's kind of compare that to the periodic table. So the periodic table for helium should say something like 4.001. Okay, so the real weight, and we're going to be talking more about this, okay, is that. All right. So let's do an example here. We should be able to kind of backtrack from this is the mass number. These are 2 forms of uranium, U-235 and U-238. Okay, one of them is great for nuclear fission, basically breaks apart. But we can backtrack from that number to particles. So here's how this would go. If these are the mass numbers, and they are, that mass number is equal to number of protons plus number of neutrons. How can we know the number of protons in a uranium atom? The red number. Okay? So actually, uranium is number 92. So both of these have 92 protons in their centers. Okay? But they differ by their mass numbers. So in one case, we have a mass number of 235. In another case, we have a mass number of 238. Okay? Do you see where we can get this number over here by difference? One of your homework problems is going to be getting that number by difference. Does this make sense? So, and again, sometimes, in fact, I have it here, just so I don't embarrass myself. Sometimes we'll actually use a calculator for these. What the heck, right? So if we pick on the uranium-235, and if the question is, which it might be sometimes, tell me the number of neutrons in this version of uranium. All I got to do is take 235 minus 92. And I get 143. So there's 143 neutrons in that, what we say, isotopic form or isotope of uranium. Let's do the other one. Let's do this one. We would take 238, which is its mass number. Mine is its atomic number, number of protons, minus 92. It looks like there'll be 3 more than that, so I'm hoping it'd be 146. Just got 3 more neutrons. Okay? Uranium's number 92. She's just double checking. Okay? This, honestly, is a good example of, if you look at, we're going to be talking more about this, again, this decimal number, but if you look at uranium, it says that it actually it has a 238.03. 238.03. So that's an average, actually, that is how much an atom weighs.
So like if that was on the test, say, then the number up in the corner is the number we'd use, but we would round it to the whole number?
No. No.
And then minus it?
Nope. If on a test, I definitely, if I'm talking about a mass number, it's going to be a whole integer. It's going to be a whole number. Mass numbers are always whole numbers. You should never use, really, I don't think, the periodic table to get a mass number, because a mass number is,
So
a mass
it's a
number,
decimal and everything.
yeah, mass number, yeah, does not have any decimals. A mass number is a counted number. It's a whole number.
So you would give it to us like this?
Yes, I would give it to you like that. I'm glad you, yes, I did
That's
not.
the
mean
part
to-
that I was
Yeah,
confused.
I didn't mean to confuse you on it. When I passed around those 2 laminated sheets, they clearly were whole numbers for, it's give the element and give the whole number. So, I mean, that makes sense. Protons and neutrons, it's a whole number. Yes. Yes. You got it. Okay. So let's do one more. I was going to do another example of what we just did. Let's pick on... Let's pick on vanadium. Okay. So, I don't think that's one you're supposed to have to memorize. So V for vanadium. V for the element vanadium. And let's just say, I'll give you a minute to do it. Let's just say that I had 2 isotopes. That's a big V, isn't it? And the number I'll go ahead and start to kind of show you. The number actually for the mass number, a lot of times we put it up here. So for the first isotopic form of vanadium, it has a mass number of 50. Okay, and the other isotope has a mass number of 51. Okay, and so the way the question in your homework is going to kind of go is like this. For both of them, I want to knock out the number of protons, and I want to knock out the number of neutrons. So I'll give you a minute. So any questions about that? Okay, so I went ahead and posted up here. Did we all get the same thing? Cool. Well, now the other variation you probably have run into more than the isotope thing, the idea of ions. So ions is where actually electrons, what we say kind of come and go. And to me, it makes sense if you're like, well, are protons going to come and go? No. Are electrons going to come and go? Yes. They are actually an electron cloud outside the nucleus. So an ion is basically you don't have the same number of electrons as you do protons in the center of the atom. So there's two possibilities of ions. There is the possibility where actually you have lost an electron or so. Now, look carefully at this fourth bullet up here. So this kind of combines something we already talked about earlier in this part. Do you remember when we said we talked about the JAG on the periodic table? Okay, so the JAG on the periodic table separates metals on the left from that cute little triangle of nonmetals, right? So already I kind of want you to start to think metals, okay? Metals tend to lose an electron or two or three. Okay, so picture an atom with its positively charged nucleus with the protons, okay, in there. It's snugged away, okay? And picture it losing an electron or so. So basically now it doesn't have the same number of electrons as protons. It's deficient, okay? So it runs around with a positively charged ion, okay? We call this, I can't believe this didn't get on my slides this summer. We call actually this a cation. Oh yeah, I did. Okay, I was like, whoa, I didn't realize that cation. Sometimes people call it, no, not really, but does it look like cation? Cation, cation? Okay. So metals tend to form cations, okay? For every electron it kicks off, it becomes positively charged 1. So we're going to actually see here in a minute that some metals like to kick off 2 electrons, and then they actually have 2 extra protons, so then they become a +2 charge. Okay, they're 2 electrons short. So, the other version of an ion actually has to do with the nonmetals. So nonmetals tend to do this. Nonmetals tend to pick up an electron or 2 or 3, okay, and add them to their already existing pot of electrons. And in doing so now, they have extra electrons compared to their positively charged nucleus, the protons. And so they actually run around with a negative charge, and they are called anions. I know. Really? Anions. It does kind of look like anions. Yeah. So again, the metals tend to form cations by kicking off an electron or 2, and nonmetals tend to form anions, okay, by gaining an electron or two. All right, look for the jag, right? So this whole idea of electrons kind of coming and going actually has to do with something we talked about earlier in this part. And actually, starting with Bohr's model, we said actually electrons around an atom in a cloud, the electrons are not created equal, that electrons exist is certain energy levels. And so we talked about this the other day, that, for instance, if we pick on sodium, okay, sodium has 2, 8, and 1. Okay, that's kind of showing you the main energy levels, where 2 electrons are hugging the sodium nucleus, okay, the lowest energy level. That energy level got full, the next 8 goes to the next energy level, that energy level gets full, and actually what is very important is this lone electron out here. Okay, we said actually you can count valence electrons, okay, if you just pick off the old-fashioned timey group number, okay, for the group A elements anyway, for group A elements, that's all up here. So all of these have 1 valence electrons, and in your homework, which is looking pretty good by the way, I just kind of glanced through it, you guys told me that these guys have similar properties. What are these, alkali metals, okay? Is it like talking? Okay. So the alkali metals have similar properties. That should do it. Oh, really? Okay. The alkaline earth metals, 2A, have similar properties. And then remember, you're supposed to know 7A are the halogens, and 8A are the rare gases. Okay? Maybe. Okay. So let's go ahead and maybe put the jag up here. So we said the jag actually kind of goes down. The jag separates metals from nonmetals. Let's find boron. Okay. Then actually over here we have the metals. And over here we have the nonmetals. Okay, and we said just a minute ago that metals are going to tend to form cations, and they will kick off, lose electrons, and nonmetals will form anions, and they will gain electrons. That's spelled gain, right? Okay. Did it just like go backwards and lose that little bit? Okay. So it all has to do with valence electrons. And what we're going to see is that these group 1A elements, they lose their 1 valence electron. Sometimes students will put a +1 charge up here at the top, okay, of the alkali metals, okay, because actually they form a +1 cation by kicking off that 1 valence electron. Okay, these guys, 2A, form a +2 cation by kicking off these 2 valence electrons. Okay, 3A form a +3 by kicking off these valence electrons. Okay, so sometimes students, like I said, will take their periodic table and kind of mark it at the top of the column. All right. Well, switching gears to the anions. Notice that I'm skipping some columns, I'm skipping some groups, because they sometimes kind of go either way. They're not entirely predictable. So now when it comes time for an element to pick up electrons, what it's trying to get is a complete set of 8 valence electrons. So starting with the rare gases, can you see that actually the rare gas, they already have 8. So I'm going to go ahead and put a I'm going to put neutral. I'll put the symbol 0 up there because they don't like to pick up any electrons. Okay, moving on to the halogens, they only have 7, so they'll pick up 1 electron. And if they pick up 1 electron, now actually they have one extra negative charge than their positively charged nucleus, and so they run around with a -1 charge. These guys, 6A, they pick up 2 electrons to get a set of 8, and now they are -2 charge. And then I'm going to stop with the 5A, the 5 valence electrons. If I want to go from 5 to 8, I need to pick up 3 electrons, and in doing so, now I am an anion with a -3 charge. That's it. Okay, so like I said, I haven't decided what we're going to, I have a couple of options for Thursday's lab. One is to kind of dive a little bit further into this with how we make compounds then. But those are the ions. Not too bad. So let's see, do you guys have the answers to these? I'll give you a minute. You'll need yes, you do already have the answers to these. You don't need a minute. So sodium, it's a 1A element, so it forms a +1 charge. Oxygen, it's a 6A element. Remember the number, when I say 6A, that means it has 6 valence electrons. It wants to become, move that 6 to an 8, so it picks up 2 electrons, so it becomes a -2 charge. Bromine is one of the halogens, 7A. 7 + 1 is 8, so it's a -1 charge. Magnesium, group 2A, so it loses its 2 valence electrons, becomes a +2 cation. Nitrogen, it is a 5A element, and so it picks up 3 valence electrons, becomes -3. Potassium, a +1, it loses its 1 valence electron, becomes a +1. Sulfur is underneath oxygen. It's also a 6A. It picks up 2 valence electrons to become a -2. Fluorine, another halogen, 7A. It picks up 1 valence electron to become a -1. Calcium, it's a 2A. It loses its 2 valence electrons to become a +2 cation. Last but not least, phosphorus is under nitrogen. It's a 5A. So it picks up 3 electrons to become a -3 charge. So there you go. I try to avoid reading slides, but sometimes it happens. So usually, kind of in a shorthand, what helps is to all at once tell which isotopic form it is. Remember, to tell what isotopic form it is, we need to say its mass number, okay? The mass number, which is, remember, that's the number of protons plus the number of neutrons. Okay, and its atomic number, we said that's the number of protons, okay, and its charge, okay, whether it's got, you know, the same number of electrons or a different number of electrons as it does protons, okay, and this symbol right here, of course, is going to be like your Ca for calcium, your K for potassium, your Fe for iron, so that X, although there is an element X in cartoons, okay, there is no real element X. The closest we have is Xe, which is xenon, okay. So we're going to do a few examples, then I'm going to kind of turn you loose with your homework. So if we pick on fluorine, the symbol for fluorine is F, okay. Now notice in this example there is no charge up there, so that means it's neutral. There's no symbol up there, okay. So we should be able to answer these questions, and you should be able to answer these questions. So what's its atomic number? You guys already had the answer here? Dang, I sure wasn't on the ball, was I? Mm-hmm. Okay, its atomic number then is, you get it from either there, okay, or the periodic table, okay? So it's always going to be 9. Its mass number is right there, 19. So I will always give that to you, okay? Number of protons is the same as its atomic number, so it's 9. And in this case, since it's neutral, it also has 9 electrons, okay? And neutrons, we did that before. Basically, you take the mass number minus the atomic number. So, of course, that's 19 minus 9 is equal to 10. That's it. down the board. The next one's a little different. It's dealing with an ion. It's a positively charged ion, so it means it's kicked off electrons, specifically 2 electrons. And that makes sense what we just talked about. If you find calcium on the periodic table, it's a 2A. It kicks off those 2 valence electrons. So protons would be, what, the 20?
Mm-hmm.
That's its atomic number. Electrons, now in this case, the number of electrons are different than protons. So actually, does this make sense? We actually have 20 minus 2 is equal to 18 electrons. Have to concentrate. If you ever, some of these, you just kind of think about it. Does it make sense? Does it make sense that it has 18 electrons? 18 electrons and 20 protons. Would that give you a positively charged ion? And the answer is yes. That's how I think of it. So neutrons, then we're going to take its mass number, which is 39, and from that subtract its atomic number, 20. And it gives you, what, 19. 19 neutrons. And last but not least is an example of an anion. So we're going to pick on chlorine, which again, if we were just in the context of what we were talking about, chlorine is a 7A element. Now, in order to get 8 valence electrons, it's going to pick up 1 electron and become a -1 charge, which is awesome. So it's always nice when things are consistent with the other things that you learned. So number of protons, since it's a chlorine species, okay, it's going to have the same number of protons as a neutral chlorine atom, which is 17. We can tell that by its atomic number. Electrons, well now in this case we would have 17 electrons if it was neutral, but now we have an extra electron because it's a it's a -1 charge, so actually it has 18 electrons. And neutrons we can get by the mass number, which is 36, minus the number of protons, which is 17. So I'm getting, what, 19? Okay, thanks. 19 neutrons.
So when this is just a minus, it's really a -1.
Right, yep.
Just fill in the 1.
Yeah,
Can we do
Grace, yep. And they do that a lot in chemistry. If there's no number after the symbol, it's just understood it's 1. Yep. So that's the same thing as a -1. All right. I guess we did have one more thing before I turn you loose with your homework. So we kind of got ahead of ourselves a little bit today. Remember we looked at helium and we said in the version of helium that I put on the board, the helium atom, since it's helium, it's got to have 2 protons, and then what I chose was to stick 2 neutrons in it. If they each weigh 1 AMU, then you got a total of 4 AMUs in the nucleus. So I'm going to turn our attention now to the decimal number in the box of for each element on the periodic table. That actually is how much an atom weighs in AMUs. Okay, so we call that the average atomic weight, the average atomic mass, the atomic weight, the atomic mass. It's all the same thing. So it's the decimal number for that element on the periodic table. The whole number is number of protons. The decimal number is how much it weighs in AMUs, which is very small. Okay. So now, how do they get that decimal number? They have to, and I'll kind of hold this up. When I passed around the different versions of an element, they have to consider, for instance, let's pick on xenon. This xenon on this little sheet of paper actually has 7 isotopes. You're like, xenon has 7 isotopes. Are you serious? So you're like, well, which one do we pick to put on the periodic table? And the answer is all of them. Basically, you do, and in my other chemistry classes we talk about this, but you actually can calculate the decimal number on the periodic table, but you have to know with each isotope how abundant is it. Okay, so for instance with xenon, I'm just kind of looking down here. I've got a 131 and a 129 isotope. and 132 that's pretty abundant. So in my calculations, that one will have to count more. So that's what we call weighted average, no pun intended. Okay, so I think that's it. Now, now this one you don't have in your blanks, right? So take a minute, find lithium, iron, and uranium. Okay, and this is just to kind of get you looking at the periodic table. You won't have to memorize that any, like the atomic number or the average atomic mass. Okay. I think we probably all got the same thing. Very good. So if you use the black and white periodic table that you're going to have for the test, so you have one of these for the test, a clean one for the test, you automatically went with 3 decimals for lithium and 2 decimals for iron and uranium. And actually, that's kind of the trend to go. Okay, so your homework is this. So we are kind of going back and forth a little bit, this chapter and going back a chapter. So on page 332, exercise number 16 and 18. And then back on page 303, exercise number 2. So I went ahead and brought screenshots for your 16 and 18. Remember that actually you have the answers to the ones ahead of them in pink here, in case you want a hint. But it's exactly what we've been talking about. For 16, it wants you to give electrons, valence electrons. Don't worry about that other part. So it's electrons, valence electrons, and shells containing electrons. Don't worry about that part. The number of shells contained, last part. but for a beryllium atom and a sulfur atom. And then for 18, just knock out the atomic mass, that's the decimal number, right? The atomic number, the number of protons, and the number of electrons for neutral argon and strontium. And then going back to the previous chapter on nuclear chemistry, this actually is a table where you're supposed to fill in the symbol, the number of protons, the number of neutrons, the number of electrons, and the mass number, just given the information that's there. So for instance, this is all about gallium, okay? How many protons, they told you neutrons, how many electrons, if you know it's neutral, what's the mass number? Of course, mass number, you're gonna add the protons plus the neutrons. If we look at the next one, you're like, dude, they didn't give me an identity. But they sort of did, because they give you 15 protons. So you're like, I'm just going to look on the periodic table for 15, and looks like that's phosphorus. Okay, so, and then fill out that. Okay, so that's kind of how that goes. All right, very good. We will see you on Wednesday.